Hello, my name is Liam Fitzhenry. Today is March 25th, 2023, and today I'm going to be talking about my design project 3 for ELECENG2EI4. So the goal of this design project was to design a linear amplifier that takes an AC source with an amplitude of 500 millivolts and an internal resistance of 100 ohms and deliver it to a 100 ohm load with less than 10% attenuation. So I have this lovely Word doc here that'll hopefully sort of outline the steps I took to design this circuit. So the first thing I needed to figure out was which topology I was going to be using. So I decided on a common collector topology, and this is for a few different reasons. So I started with this overall gain equation, which basically describes the gain of the overall amplifier in sort of three parts. So we have a voltage divider here with the source resistance of the source and the input resistance of the amplifier. And then that voltage is again divided further with the output resistance of your amplifier and the load resistance that you're using. And you can kind of think of this AV0 term as like the intrinsic gain of the amplifier. So that's as if there were no internal source resistance, no load resistance, and you sort of just delivered the input directly to the base of the transistor. So I have this equation here, and then I sort of looked through the properties of the three different amplifier topologies that we studied in class. And the common collector stood out for a few different reasons. The big one is that it always has a gain around 1, so less than or equal to 1. Which is sort of exactly what we're looking for here, right? Because a 10% attenuation in signal means that the gain has to be larger than 0.9. So yeah, that's check right there. And then the second thing I noticed about the common collector is that it always has a moderate to high input resistance, which is going to be really helpful in this term here. Because we want our gain close to 1, we want every term in this equation close to 1. So here our RS, our source resistance, is set to 100 ohms. So we can't change that, and we want this fraction to be as close as possible to 1. Therefore, we want our Rin value to be much larger than this RS, such that this fraction gets as close to 1 as we can. So that's another check there. And then finally, the common collector amplifier also has a small output resistance, which is helpful for this term because our RL is set to, again, 100 ohms. So we want to get this fraction as close as possible to 1. Therefore, we need our Rout value to be much smaller than RL. So those are sort of the three different properties I looked at in order to choose the common collector topology over the others. Okay, so we're not quite done yet designing because we need to figure out if we're going to use a BJT or a MOSFET in our common collector amplifier. So what I first noticed was that this common collector gain equation, so now that we've picked our topology, we can substitute in the more specific equation here, has GM terms in this final fraction here. So our overall gain is our voltage divider with our input resistance and our source resistance multiplied by this term here. So this 1 is obviously a fixed value, and we want this fraction to be as close as possible to 1. Our RL is also fixed, so therefore we want GM to be much larger than 1, such that the numerator and denominator of this fraction are approximately equal. So therefore we want our GM to be very high. So if we look at our two equations for GM for our MOSFET and our BJT, you can see the MOSFET one involves square rooting the drain current with this K value, which is always pretty small, whereas the BJT one multiplies by 40. So in general, the transconductance parameter, this GM, is going to be much larger for a BJT because instead of square rooting the drain current, you're going to be multiplying it by 40. So collector current and drain current here, I assumed were sort of synonymous. So I went with a BJT because in general it's going to have a much higher GM value. Okay, so I've decided that I'm going to use a common collector amplifier with a BJT, but I don't have any values for my resistances. All I have is for source and load. So if I sort of sneak peek ahead here, we're going to have these two resistances that help to DC bias the circuit to get the correct values at the output that we want. So I need to determine the values of R1 and R2 because RS is set and RL is set. You can just ignore the capacitors for now. So the first thing I need to do to find those is to find the range of GM that will be acceptable for the parameters, like the requirements that we're looking for in terms of gain and voltage amplitude, input amplitude. So GM, I can calculate from this equation. So we know that our input voltage amplitude our amplifier has to work for input voltages of at least 500 millivolts. So we can sub that in here for our amplitude of VI. And then this equation here is taken directly from the formula for the common collector amplifier. So we have VT as 25 millivolts at room temperature, 1 plus RL is set to 0.1 kilo ohms, and GM. So rearranging this formula around, we can solve for the value of GM. So GM has to be greater than or equal to 990 millisiemens in order for this condition to be satisfied. So the amplifier will work for input amplitudes of at least 500 millivolts if our GM value is greater than or equal to 990. So this GM value is a direct function of the DC collector current. So like I said here, GM is 40 IC, therefore IC is GM over 40. So we divide this number by 40 to get that our DC collector current will be bigger than or equal to 24.75 milliamps. So this is important, so I'm going to leave it in bold for later. Our second equation that we need to consider is our gain. So our gain, this AV here, has to be larger than 0.9, right? Because we want less than 10% attenuation. So we're going to stick this gain equation in here from our common collector gain formula that we had earlier, and we're going to sub in everything that we know. So at this point, we know GM. We're going to say it's 990. We're going to set it to the minimum possible value, such that all values above 990 will satisfy this equation as well, because this side is greater than that side. And then we know RL, we know RS. The only thing we don't know in this equation is RN. So you can rearrange this by multiplying this term over there, and then we end up with a linear equation for RN, which we can solve, and it comes out nice and easily to that our input resistance has to be greater than or equal to 1 kilo ohm. So we have a few conditions here that we're going to take into our sort of next stage of the analysis. And at this point, I kind of drew up a schematic in LT Spice to sort of help me visualize some things, because it's going to be helpful moving forward. So like I mentioned, here's our input, our source with the source resistance, and this capacitor just helps cut it off in the DC case. So capacitor is open circuit in DC, but this AC voltage has no effect on the biasing of the transistor. And the same thing for our output voltage over here. So when I set up here that Rin has to be greater than or equal to 1 kilo ohm, that's not just the input resistance of the transistor. That's the input resistance as seen by the source. So you also have to include these two resistors in that calculation. So when we sort of simplify that, it turns out the R1, R2, and the input resistance of the this transistor, which I'm going to call Rn prime, are in parallel. So the overall Rn, which is these three values in parallel, will be greater than or equal to 1K. And then from there, we can sub in our common collector formula for the input resistance, which is R pi times 1 plus GMRL in parallel. And I'm going to call this X for now, just to simplify things a little bit. So R1 in parallel with R2 is going to be X. And again, simplifying here using our small signal model, you know that R pi is equal to beta over GM. So this is sort of the first time I need to go look at the data sheet for the transistor that we're using, which is this 2N3904, to determine this value of beta, because this is a property of the transistor. So if we go over to the data sheet, which I'm not sure if you can see, so I'm going to quickly, yes, I think you can see that. Okay. So if I jump over the data sheet here, I'm going to scroll all the way down to these graphs, which are very helpful. And this is the one I'm looking for. So this HFE current gain, so beta is proportional to the current gain because IC is beta IB. And then we have sort of that plotted with our collector current. So it's not totally constant with the collector current, but it's okay. So I went with just sort of a value in the middle here, about 100 to be safe. Keeps it a nice even value, and it should work for all values bigger than that because, like we mentioned, our collector current is going to be about 20 milliamps. So we should be good on the low end with beta as 100. So we're going to go back to our equation. We're going to sub in 100. We know GM is 990. We know RL is 0.1. So this whole term here will simplify to 10.10. And that's in parallel with X. Our other two resistances parallel to be bigger than or equal to 1. And then, so doing a little arithmetic, solving that equation, we get that X is bigger than or equal to 1.1K. So the parallel combination of R1 and R2 have to be bigger than or equal to 1.1 kiloohms. Okay, that's our first sort of hint in figuring out these two values. The second thing we use is that collector current that we determined earlier on when we found the value of GM. And we're going to use that in our DC analysis. So DC analysis, we get rid of that source, like AC source like I was mentioning, because there's a capacitor in the way. And then we're just left with R1, R2, RL, and our VCC, our supply voltage. So the first thing I'm going to do is going to approximate IE with IC. IE is going to be a little bit bigger than IC, so we're going to call it 25 milliamps. And we're going to keep this inequality just for now. And so the first sort of calculation that I'm going to do is going to solve for the base voltage. So that's just simple KVL. So here's 0. We're going to go up by RL times IE here, and then we're going to go up by VBE. Because the emitter is the base. So that's the second time we need to go to our data sheet to find that value. So we scroll up to our, just up here. Of course, I can't find it right now. Here it is. Okay, on characteristics. So we're going to assume that our transistor is in forward active because it always is in small signal analysis. And we're going to go down to our base emitter saturation voltage. So we're given a few different values. We've got min, max, and then it also is slightly dependent on your collector current. So I went with a value sort of in between all of these. I went with 0.75 just because it's in between these two different values. So we'll go back here and we're subbing 0.75 for our voltage jump across this junction here. And solving that with subbing in 0.1 here, subbing 25 here, you get that VB is about 3.25 volts in the DC case. The second thing I did was use a KCL equation to find sort of to relate these three currents on the left side of the diagram here. So we're going to call this one R1 going down here. R2 will be going from VB to ground through R2. And then IB is, of course, going into the base because this is an NPN BJT. So using KCL, we find that I2, this current here, is the sum of, this current here is the sum of these two. So we can rearrange that to get I1 minus I2 will be equal to IB. So using Ohm's law here, we know that this node is 5 volts, this node is 3.25 volts, this node is 0. So we can say that I1 is 5 minus 3.25 over R1, I2 is 3.25 over R2, and then this base current here is IE divided by beta plus 1 by the amplification characteristics of a BJT. So like we say, IC is beta IB, then we can say that IE is beta plus 1 IB, therefore IB is IE over beta plus 1. And we're just going to simplify our this side of the equation a little bit to get that 1.75 over R1 minus 3.25 over R2 is equal to this number here. So this is just subbing in our beta equals 100 again over here, and our IE is 25 milliamps. So at this point, we have this equation with R1 and R2, as well as this equation with R1 and R2. So two equations, two unknowns. This is an inequality though, so it's going to help us out a little bit. We're going to pick a value for R1. We're going to make it nice and easy at 10K. I picked a pretty high resistance here because I knew that the parallel combination of R1 and R2 is going to be bigger than or equal to 1K. So might as well go a little bit high on the high end. And so sub in R1 is 10, rearrange, solve for R2. The R2 is bigger than or equal to 45K. So just to make it simpler on myself, during circuit construction with like the breadboard and everything, we're going to say R2 is 50K, just because it's pretty close to this number here, but it is bigger than, so it satisfies this inequality. And then finally, we're going to check this with our other equation over here, just to make sure it still satisfies. So we're going to make sure that 10K in parallel with 45K is bigger than or equal to 1.1, and it is. So those resistances should be good for this circuit. So the next thing we need to talk about is how I simulated my circuit in LT-Spice. So I kind of mapped it out like I showed you earlier on with the resistances, the transistor, capacitors, and our voltage sources. The big question is here, which transistor model did I use? So I simply just went to go place a component, used an NPN transistor, and then clicked on the pick new transistor, and the one in our component kit was second from the top, so it was not that hard to find. And you can see the name here, 2N3904, matches up with the name in our component kit. So the next thing to determine was what kind of simulation I was going to be running, and I decided on doing a transient simulation with a stop time of 1 millisecond. That was mostly based on the frequency I chose for my source. I knew it had to be high enough that these capacitances would have extremely low impedance in the AC case, such that they wouldn't affect the circuit analysis. They would just become a short circuit. So I figured 10K was pretty comfortable, considering we're using a pretty small capacitance of 100 nanofarads. Okay, so if I go ahead and simulate here, and I plot our V in node and our V out node, and I'll change the color of this one just to make it a little bit easier to see. We can see that they're pretty close, which is exactly what we're looking for. We're looking for a gain of at least 0.9, and we know it's going to be less than 1 because we're using a common collector topology. So just from visual inspection, that looks pretty good. But just to double check, we're going to add a trace. You can see this window here. We're just going to add V out over V in. Okay. And it sort of does a weird plot because it's going to be dealing with some asymptotes, because it's going to be dividing by 0 as these lines cross 0, which is a little unfortunate. But what we can do now is just edit it such that we go manual limits. Set the top to 1.5, let's say, bottom to 0. We're going to take it out to 0.1. You can see here that our gain, it looks kind of all over the place at a first glance, but once you look past the fact that there's going to be asymptotes every time our Vin crosses 0 volts, it's actually pretty solidly at around 0.9. So if I attach a cursor and I grab it here, and the window popped up on this monitor, but if I take our cursor and I look in sort of the middle portion of our gain curve, which is particularly linear, we can see that our vertical value is around, so it's converting it to milli, which is unfortunate, but 900 milli is about 0.9. So we can see that it stays above 0.9 this entire way, and it only drops below 0.9 when it goes down into this asymptote. So I feel pretty confident this is good because we're going to get a pretty big, our biggest voltage discrepancy between input and output is going to be at these peaks here, And if I put it right at the peak where there's a gap there, it might be like slightly concerning if you're not sure if it's more than 10% attenuation. I can just look at our gain equation and find out that it's still only about 4% attenuation. So I feel pretty good about that, and I think I'm ready to move on to the physical circuit. Okay, sorry, one final thing that I want to touch on before we exit the simulation part of the project is determining the input resistance of our constructed amplifier. So simply to determine this, I just plotted our input voltage from this node here, and I inserted a math channel on our plot here. That was the input voltage divided by this current in this, so the input current basically. You can see this negative sign here because LC Spice by default has current going left, or at least it does in this case. I don't know how to change that, so I just threw a negative there just so that it would be the current going this way. So input voltage divided by input current. Again, we're going to have some weird spikes here when the voltage crosses 0, or when the current crosses 0 in particular. So what we're really interested in is just the sort of average value in the linear region of this red line here, which we can see in most cases is approximately 6.5 kilo ohms. So in every cycle of the voltage, we're looking at somewhere between 6.4 and 6.5 kilo ohms, which again will satisfy the condition that we determined earlier, that the input resistance needs to be bigger than or equal to 1 kilo ohm. So yeah, just further confidence that this circuit will work, and we can move on to the construction. Okay, now I'm going to show you my physical circuit. Here's my student card, and today's date is March 25th, 2023. And please excuse the shaky camera work. Okay, so we got our 82 here, our breadboard here. We're going to start with showing you where this is our AC source here, this red wire, which is going to be connected to the power rail on this side of the breadboard, this red power rail here. And this orange wire here is going to be connected to our 5-volt supply from the 82, and that goes all the way up and down this red power rail on this side. And our ground, this black wire here, is connected to the blue rail, the blue ground rail on this side of the breadboard. So where do we want to start? Let's go with the AC voltage first. This red wire, so just like in our schematic, it's going to be first connected through this 100 ohm resistor here, through this 100 nanofarad capacitor directly into the base of our BJT, which is this little black thing right here. Also connected to the base of the BJT, first is our 10K resistor, which is this one sort of sneakily placed right in there, which is connected through this green wire to our 5-volt supply, like in the schematic. And then we also have our 50K resistor, which I implemented using two 200Ks in parallel, which is grounded through this orange wire right here. Let's go now to the source of our BJT, which is simply just this orange wire. The source is, sorry, not the source, the collector of the BJT. The collector of the BJT is directly connected to VCC through this orange wire here. And then finally, the emitter of the BJT is this red one right here, which is connected through our load resistance, which is this guy right here, to ground. And then our output voltage, which is this brown scope. This brown wire goes into the scope of the 82, channel 2, and it's connected through this coupling capacitor, 100 nanofarads right here. And again, our other scope is just directly on this, so it's this yellow wire here, it's directly on the power rail on the side of the board, which is our AC supply. So channel 1, AC supply, channel 2 is our output voltage here, and then of course both of these 1 minus and 2 minus wires are connected to ground on this side as well. Okay, so I've got my circuit constructed on the breadboard. Now I'm going to head into waveforms to form some measurements. First, I'm going to show you my supplies. So I've got my positive supply at 5 volts. I'm not using my negative supply. And then I've got my wave gen set to a sine wave with a frequency of 10 kilohertz, amplitude of 500 millivolts, and an offset of 0 volts as specified earlier. Now I'm going to scope it as I mentioned. I've got channel 1 as our input voltage and channel 2 as our output voltage. And just sort of by visual inspection, you can see that they're fairly similar, but just to make sure that this attenuation is in fact less than 10%, we're going to perform a few calculations. So the first thing I did was add this math channel here, which is simply just C2 over C1. So V out over Vn, this plots the gain. Again, with in the same sort of manner as the schematic, when these curves approach 0, we're going to have some asymptotic behavior, which sort of ruins the plot a little bit. But what we're really looking at is just sort of this linear-ish region when these curves are not close to 0. So how I measured this was simply by just including a measurement of the average value of our M1 channel. Where, if I can stop at any time, you can see that it's about 0.94. So that corresponds to an attenuation of about 5.7%. But just to be sure, because I wasn't super confident in this method, I also included measurements of the peak-to-peak voltage of C1 and C2. So again, if I stop this at any time, and I can pull up a calculator, then we can do the division manually. So C2 over C1, so 0.9678 divided by 1.01. And you can see this gives us, again, an attenuation of less than 10%. This one's about 4%. Yeah, so I'm pretty confident that this meets the standards or the requirements of what we were going for. Okay, so one other way we can check the linearity of our amplifier and make sure that it's working properly is to check out the spectrum analysis, or the frequency spectrum of both the input and the output signals. So we pause at any time, we can see that the frequency is plotted here on the x-axis, and the amplitude of the signal is plotted on the y-axis in dBV. So what we'd expect is a big spike at 10 kilohertz for both signals because they are in phase and linear. And we can see that's the case for both C1 and C2. And it goes to about -8, -6 dBV, which corresponds to 0.5 volts. So that's what we expect. We expect both signals to be made up of mostly a 10 kilohertz sine wave. And as you can see, the rest of this, there's no real outliers. So if I let it run, this spike remains constant here, but nothing else pops up. This is really just noise. So this is a good sort of indication that our input and output voltages are linear and have a gain of about 1.